Okay. Hello, we are the Distributed Electric Propulsion Green Team from the University of Central Florida, and this is our Senior Design Showcase project. My name is Joseph Hoayun. I am the team lead, the manufacturing design consideration, materials and vendor researcher, team communications, and scheduling coordinator.
Yeah, I'm Matthew Emmerich. I'm in charge of wing design, 3D modeling, and the FEA material static structure testing.
My name is Matthias Tice. I was part of the airfoil decision matrix, the wing design, the control surface design, stability, and part of the manufacturing and design considerations.
My name is Chris Carlson. I worked with Matthias on the airfoil design and wing structures. I reviewed the FAA regulations and legalities, as well as doing flow analysis on SolidWorks.
Hi, I'm James Garninsky. I was in charge of radio control, electronic spatial awareness diagram, and electronic components.
Hi, my name is Kevin Merrick, and I dealt with fuselage design, structural design consideration, and mechanical systems design.
So for our project objective and mission was to design, manufacture, and test a highly efficient DEP aircraft that can take off and land safely. We wanted to have at least 6 motors to power the aircraft and have a minimum flight of 3 minutes and have a wingspan of 39 inches. The deliverable for the minimum wingspan was given to us as 36 inches, but as a team, we decided to make the smallest wingspan as possible to stay under budget and reduce the amount of problems that can occur during the manufacturing process. From last semester and this semester, we have reached out to get feedback from people in the engineering field to gain a different point of view in the design of our aircraft. For example, speaking with Mr. James, who is a test engineer at Lockheed Martin, he mentioned to make the rudder size from our original design bigger to increase the control surface area. Another person who we reached out was Dr. Osbe, who is an aerospace professor at UCF. He gave us many good points from our DEP aircraft from Senior Design 1 to Senior Design 2. In the exploded view of the CAD drawing, this is our aircraft. Most of our parts were made out from Coruscant foam. Coruscant foam is a structural foam used with that's high toughness and impact resistant. It is a high performance foam, ideal for marine applications. So the material we use to manufacture the fuselage, ailerons, horizontal and vertical stabilizers is Coruscant foam. The wings were made out of multiple materials. The ribs and aileron hinges were made out of balsa wood and laser cutted. The motor mounts and square wing base were 3D printed and made from PLA plastic. Propellers are plastic, and the square and circular spars are carbon fiber. We wanted the wings to be hollowed out to allow wiring to flow through. Also, if there were any damaged part of the wing, if we were to make it out of foam, we would have to replace the entire wing, whereas the design we have now, we would only have to replace a small section if the part was damaged or it needs to be moved. Lastly, the landing gears for the aircraft is made out of aluminum.
Here we have the slight redesign for the wing base. We've added the structural anchor points for the fuselage attachment to the landing gear with bolts. We also included wing spar attachment points that account for the dihedral in the wing design of about 3 degrees. Not only that, but we also included an angled top to assist in the 3D printing process so that we didn't have to remove supports from the inside of the holes.
This is the diagram of electronics. I decided to use one ESC per motor to reduce the risk of having unevenly distributed thrust. To reduce the risk of voltage drop, I picked ESC that has 20% more current than motor can draw and battery that has 20% more current than total current of all ESCs can draw. We also decided to use gyro for stabilization. Per pound and thrust to weight ratio calculations I have done. It's more than we need. I have decided to have more thrust than we need since the most of electronics were used and used electronics drop performance over the time. This is the flight duration calculation with the maximum throttle. It was 4.2, which we plan to use only 70 to 80% of throttle, so it can fly more than this. We tested all motors more than 4 minutes on the ground, and we did not encounter any problem. ESCs did not fit at first. because of bulky battery cables and Y cables. We cut them off and soldered them parallel to make it fit neatly, as it's seen in the picture. Also, motor cables were bulky that didn't go through the ribs. We cut it and added thinner cables, made it go through the ribs.
To start off with the control areas, for the control surface and the ailerons, we did a very traditional design in most RCs where you put the servo into the wing and then you have a small triangle or L-shaped bracket hooked to the ailerons, and that's how you control it, and this works magically. In the tail, we originally wanted to put the servo nearest the tail to help with the least amount of air in the movement, but then later, which I'll talk about in a second, we were having problems with our center of gravity, and we were forced to move our servo into the middle or close to the middle of the fuselage. Speaking on the center of gravity, we initially made our design, and in all of our CADs and theoretical design, we didn't really consider where we were going to place the wires and glue and battery and speed controllers. We were just planning to move those things as we go. And with our initial plan, putting the weight forward as possible, we were still about an inch behind the center of lift. And as we've learned, you're supposed to have your center of gravity in front of your center of lift. So we ended up moving the wings back about 3.5 inches, and this helped us put their center of gravity about 1.5 inches in front of our center of lift.
We also chose a tricycle gear setup because it's easier for the pilot to manage, especially with us being experienced at drone flying. We wanted something as easy as possible. With the tail wheel setup, it's a greater chance of a ground loop while landing and damaging the aircraft.
The majority of the plane stability comes from the tail, where it creates most of the positive stability. And although we didn't have any problem using the ratio diagram in the middle to place our tail and some of the sizing, we had troubles with controlling some of that stability. As you can see in the top left, we have very small elevators and rudder, and this made it very difficult for us to control the air. We had a bench test where we moved these surfaces with lots of wind going across them, and we saw almost no inflection on the tail. So we upped them incrementally and coming up with about a 3 times the elevator size to get us the amount of stability and control we needed.
For airfoil calculations, we just started with research and found that Carquois is a popular design for a lot of home-built RC aircraft. And then 6412 and 5414 were also just well researched and well understood and recommended through airfoil research. In XFR5 and Xfoil, we found that 6412 would work the best as far as the CL over CD for our angle of attack range. For the wing shapes, we did that all in XFR5. We used the ratios that we found in the diagram earlier. Ended up settling on this. It was getting about 39-inch wingspan with a chord of about 4.5 inches, at the ends of the wing, but about 6 inches at the base of the wing.
We chose the taper wing design. Actually, originally we chose the straight wing design because it gave us the most lift, but it wasn't the most efficient. And as we looked towards the most efficient, we chose the elliptical, but this was much more hard to manufacture. So we ended up going with the taper design to cut those in half, and ended up still being nearly as efficient as the elliptical, but much more efficient than the straight.
For our airspeed calculations, our most important was figuring out our stall speed to make sure we could get off the ground. We got about 10 meters per second or 33.5 feet per second, which was achievable based off our thrust calculations. And then we confirmed this during our test flight.
Here you can see the FEA testing model. The initial calculation for the overall weight on the spars that's distributed is about 0.324 pounds. This includes not only the balsa wood, but also the motor mounts and the motors themselves. Just as a conservative estimate, I rounded up to about 0.5 pounds. And ultimately, this gave us about a displacement of about 0.601 millimeters, which is ultimately negligible.
For our fuselage conceptual design, we began by using drafting techniques and 3D drawings on SolidWorks. The fuselage was broken down to components of its nose, body, and tail. Characteristics such as wing to fuselage ratio, fineness ratio, and ranges were made out as follows. SolidWorks was used to carry out the 3D drawing of the draft. Using Corcel foam, we took the route of shaping it with its layers. There were 3 fuselage iterations. The problems we encountered throughout our process included accounting for enough space of electrical components, the durability of the tail and body, and accounting for proper center of gravity and weight distribution calculations. For our last iteration, a carbon spar was added to the tail and resolved any forms of notable deformation. The fuselage also proposed a increased capacity bay allowed by a unique material compound that provided additional structural rigidity and support. This added room allowed for movement of its internal components to adjust their weight distribution accordingly.
Here for the mechanical hinges part, you can see the circular spar at the back end of the tapered part of the wing not only provides extra support for the tapered ribs to prevent them from twisting, but also an axis for the aileron to hinge around.
Here are some scientific tests that we did throughout our manufacturing process. Thank you, and I hope you enjoyed our presentation.